So you must be aware that a lens basically has two refracting surfaces. Okay. And when we consider a thin lens, basically what we assume is that the gap between the two refracting surfaces, okay, this one and this gap that is there, which we call as the thickness of the lens, we ignore it. We assume it is negligible compared to the object distance, radius of curvature of the lens, and such distances. The thickness is considered negligible. Okay, that is what we mean by a thin lens. Later, we'll also discuss what to do if that thickness is significant. For now, let's ignore it. So lens is basically an optical instrument which can allow light to pass through it. Light enters from one side and leaves from the other side. So it strikes one surface before entering the lens. There it undergoes refraction. And while leaving the lens also, it goes through an interface. There it undergoes another refraction. So when light passes through a lens, it refracts twice. Fine. And we will consider the lenses to be spherical lenses, means each surface of the lens is part of a sphere. Fine. Can one of you quickly tell me the spherical surface refraction formula? Relation between object distance and image distance from a spherical surface. Okay. It is mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. Okay. Mu1 is the refractive index of the medium in which the incident rays are traveling, and mu2 is the refractive index of the medium in which the refracted rays are traveling. Okay. Now consider a lens like this. Let's consider a convex lens. Okay. Actually, we should call it biconvex because both faces are bulging out. Okay. So it's a biconvex lens. Let it be. Now the left side surface of the lens, okay, the left surface of the lens can be assumed to be part of a sphere like this. The left surface is part of this sphere and its center is somewhere here. Okay. Let's call the left surface as S1. This is the center of curvature of that surface. We'll call it as C1. And the right face of the lens is part of a sphere like this. And its center seems to be somewhere here. It's not necessary that the radius of curvature of one face of the lens is same as the other. Fine. Anyway, for the right surface, which we are going to call S2, the center is here. We'll call this as C2. So this kind of visualization is important. You need to imagine the faces of the lens as parts of spheres. Okay. Let's draw a line connecting these two centers. Center of curvature. Okay, this is the line joining the center of curvature of the left surface or first surface and the second surface. And for a lens, this is what we call as the principal axis. Okay. Now, the midpoint of the lens is called its optical center. We are going to denote it by P itself, but in case of a lens, it's not called a pole, it's called the optical center. Fine. Now, what we first need to derive is a relation between object distance and image distance. Now see the surface S1, the left side surface, it has a certain radius of curvature or R1, and the right side surface has a certain radius of curvature, let's call it R2. Assume there's an object present on the left side of the lens, somewhere here. Light from the object, if you imagine it traveling forward, one ray strikes the lens along the normal, it undergoes normal incidence, and such a ray does not bend. We know that. So the light first enters from air into the lens or from outside medium into the lens through the surface S1. Then it passes through the lens material. And then at the surface S2, it leaves the lens material back into that medium. Okay, so light travels like this. The surface on which the first refraction happens is called S1, its radius is called R1. The surface where the second refraction happens is called S2, its radius is R2. Let it be. We are trying to derive a relation between object distance, image distance. No, so it will definitely depend on how the light is bending, and how much the light bends depends on refractive indices. Okay, outside the lens, let the refractive index be n1. Okay, refractive index of the medium outside the lens, let's call it n1 on both sides of the lens. And inside, I mean, the material with which the lens is made, it could be glass, it could be plastic. Many possibilities are there. It can be filled with water also. Okay, let's call it as N2. So outside medium refractive index is N1, lens material refractive index is N2. Both the media allow light to pass through them. Okay. So we discussed this idea in the last class. When light undergoes multiple reflections or refractions, the image formed by the first reflection or refraction behaves as an object for the second one. We are going to use that idea here. Okay. So let's say light strikes the first surface. Then at surface S1, light enters from outside the lens into the lens. Okay. So for surface S1, mu1 will be N1 itself, because for surface S1, incident ray is traveling outside. Refracted ray is inside the lens. Okay. So mu1 will be N1 and mu2 will be N2 for the first refraction. Okay. And the radius of curvature is R1 for that surface. Therefore, you can write mu2 by V. This V is the image distance from the first surface. This is not the final image. This is the image formed by the first refraction. Okay. So we are going to call it as VT, temporary image. This is not the final image. So mu2 by V minus mu1 by U we will take as it is, because that is the original object distance. Okay. Whatever is the object for the first surface, that itself is the object for the entire lens. Okay. So first surface object distance itself is the lens object distance. We'll take U as it is. So mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. R is R1. Okay. And see, we are applying the spherical surface refraction formula directly, right? That means these values are already substituted considering the sign convention. You don't now you don't have to bother whether you have to put a plus or a minus. Okay, these are not magnitudes. These are the, I mean, this is the formula that we have written here. So it includes sign convention already. When you substitute, you are supposed to substitute with sign. Okay, that is what it means. Now from this, what do we get? We get where the image is formed by the first surface. Okay, this VT is the image distance from the first surface, temporary image. Okay, so we can, okay, we'll put it like this. We'll leave it like this. Let this be the first equation. Any doubt in this so far? We just wrote the spherical surface refraction formula for the first surface of the lens. Okay. Now light travels through the lens and then it undergoes another refraction at the surface S2. Fine. Then at surface S2, from where to where is the light going? It is going from inside the lens to outside. Okay. So for surface S2, incident rays are traveling in the medium of refractive index N2 refracted rays are in the medium of refractive index n1. Okay, now you apply the spherical surface refraction formula. The formula is mu2 by v. Okay, here mu2 is n1. So n1 divided by v. V is nothing but the image distance, and image distance from the second surface is the image distance of the lens. That is what we are looking for. Okay, so we'll keep v as it is. So mu2 by v minus mu1. Mu1 is n2 divided by u. U is the object distance according to the formula. The object distance for the surface S2, okay, I should not say distance. The object for the surface S2 is the image formed by the surface S1. Okay, that idea we had discussed in the last class. Suppose the surface S1, okay, upon refraction from surface S1, let's say the light tends to converge here, and this is where it tends to form an image. That image becomes the object for S2. Okay, but in the formula we need distances. S1's image distance is this much, as you see in the diagram. If that behaves as an object for S2, S2's object distance will be slightly shorter. Okay, but what are we doing here? We are considering a thin lens. If you consider a thin lens, as I said, the thickness of the lens is ignored, then the image distance from the first surface, I'm talking about the distance now. Image distance from the first surface will be equal to or almost equal to the object distance for the second surface. Okay, so whatever formula we are going to derive now is valid only for thin lenses, not for thick lenses. And in problems, when they just say lens, you should assume it's a thin lens. If they want to ask you about a thick lens, they'll have to specify its thickness. Fine. So this is where that assumption of thin lens matters. Image formed by the first surface is always object for the second surface, whether it's a thin lens, thick lens, glass slab, whatever it is. Okay. But image distance from the first surface will be equated to object distance for the second surface only if it is a thin lens. Okay, so mu2 by v minus mu1 by u. Object distance for second surface is nothing but image distance for the first surface, that is the temporary image, is equal to mu2 minus mu1 divided by r. For the second surface, the radius is r2. This is the second equation. And what we will do now, we want a relation between the original image distance and the final, the original object distance and the final image distance. So we need a relation between u and v. So we have to eliminate vt, that temporary image distance. So we'll take n2 by vt from the first equation and substitute it in the second equation. So what does it become? n1 by v stays as it is, minus of n2 by vt will be n1 by u plus n2 minus n1 by r1 is equal to n1 minus n2 by r2. Okay, so we got a relation between the object distance and image distance from the lens altogether. So if you simplify this, you get n1 by v minus n1 by u, that is n1 into 1 by v minus 1 by u. Okay. From the left hand side, you have minus of n2 minus n1 by r1. If you send it that side, it becomes plus n2 minus n1 by r1. And on the right hand side, there is already one term n1 minus n2 by r2. So this can be written as n2 minus n1 into 1 by r1 minus 1 by r2. So n1 into 1 by v minus 1 by u is all this. When you substitute values in this formula, you are supposed to substitute with sign convention. Sometimes u may be positive, sometimes it may be negative. Sometimes r1 will be positive, sometimes negative. R2 also sometimes positive, sometimes negative. You'll have to substitute accordingly. Now send n1 also that side. Finally, what you get is 1 by v minus 1 by u is n2 minus n1 divided by n1 into 1 by r1 minus 1 by r2. So what we have here is the relation between object distance and image distance for a thin lens. Okay. Remember, we have used the fact that the two surfaces are very close to each other. Okay. So this is valid only for thin lens. Fine. So any doubts in the derivation so far? We are just applying the spherical surface refraction formula twice. Once for the first surface where light refracts, and then for the second surface where it refracts. We are ignoring the distance between the two surfaces. Okay. Next, focal length of a lens. Rishi, how do we define focus? How do we define focus?
Where like the parallel rays meet, or
Okay. How to generate those parallel rays? Where will they come from?
they come from after reflection.
No, no, no. Before refraction, they'll be parallel. After refraction, where they meet is called the focus. But before refraction, where do those parallel rays come from?
Infinity.
How, practically, how to make that happen?
Very far distance, sir.
Okay, infinity very far. Okay, okay, fine, fine. You just have to place the object very far. What distance is very far? It has to be a large distance compared to the radius of curvature of the lens. Okay, that's all. Okay, fine. So basically, not just for a lens, even for a mirror, focus is the image location when object is at infinity. Okay, or what you said is also correct. Is the point where the reflected or refracted rays converge in case of parallel incident rays. Okay, incident rays should be parallel to the principal axis. In that case, wherever the reflected or refracted rays converge is called the focus. Okay, so if you want to find out the focal length is nothing but the image distance when object distance tends to infinity. Plus infinity minus infinity doesn't matter when you substitute in the formula. Okay, therefore, let's use the formula that we just derived. 1 by f minus 1 by infinity is equal to n2 minus n1 whole divided by n1 into 1 by r1 minus 1 by r2. See, in some books, they write it as n1 minus n2. They interchange these two terms and then they interchange these two also. Okay, so don't get confused. In one bracket, if you have taken 2 minus 1, in the other bracket, you have to take 1 minus 2. Remember it like that. If it is n2 minus n1 that you have written in the first bracket, then it will be 1 by r1 minus 1 by r2 in the second bracket. Okay, so this tends to 0, 1 by infinity. That's all. This is the formula we use to determine the focal length of a lens. And why do we care about focal length? It helps us in ray diagrams. Okay, if you know the focus, it helps us draw the ray diagrams, and it helps you find out what kind of image will be formed and all those things also. Basically, it simplifies the formula for us. Effectively, the whole right hand side of the formula that we derived is now 1 by f. Okay. So using this formula, you can determine the focal length of a lens. And reverse. If you need a lens of a particular focal length, using this formula, you can determine the radius of curvature of the surfaces of that lens. Okay. So this is called the lens maker's formula. Okay. Now, whatever relation we derived between v and u, the whole right hand side effectively becomes 1 by f. Therefore, we can now write 1 by v minus 1 by u is equal to 1 by f. This is called the length formula. Okay, just like mirror formula, we have a length formula. And remember, both these are valid only for thin lenses. Fine. Let's solve some problems based on this. Let's consider this lens itself. Basically, we'll develop a proper understanding of image formation by lenses. Okay. Let's assume light is incident from the left side. If light is incident from the left side, the left surface becomes the first surface and the right surface is the second surface. You can take some incident rays like this. Let's say they are incident parallel to the principal axis. Okay. Now they'll undergo two refractions and they may converge, they may diverge. Depends. We don't know what exactly will happen to them. It depends on the refractive indices. Okay. Assume outside medium is air. So outside the lens, the refractive index is 1 on both sides. And assume the lens is made of glass whose refractive index is 3 by 2. Fine. The left side surface, let's say its radius of curvature is 20 centimeters. Plus 20 or minus 20, you will have to decide. And the right side surface, let's say its radius of curvature is 10 centimeters. Okay. Derive the focal length of this lens. The formula is 1 by f is equal to n2 minus n1 divided by n1 into 1 by r1 minus 1 by r2. Okay, I got two answers. One has 40, one has 40 by 3. Rishi, any answer?
Sir, I'm still solving.
Okay, fine. So in this formula, can any of you tell me what n2 means and what n1 means? Like which refractive index is n2 and which one is n1?
And 3 by 2.
N2 is that of the lens and N1 is that of the medium outside the lens. Okay. So in this case, it becomes 3 by 2 minus 1 divided by 1 multiplied with 1 by R1. R1 is the radius of curvature of the first surface where the refraction takes place. And since we have assumed light rays to be incident from the left side, this is the first surface for us and the other one is the second surface. For the first surface, the radius of curvature is 20, that's fine, but we have to substitute it by following the rules of sign convention. Radius is taken from the surface to the center, okay, in case of a lens, from optical center to the center of curvature. For the surface S1, okay, looking at the way it is curved, we can tell that the center of curvature is on this side. Okay. And according to the rules of sign convention, the direction to which the incident rays are traveling is the positive direction and the opposite direction is negative. So since C1 is on the positive side, R1 will be substituted positive 20 minus 1 by R2. R2 is the radius of curvature of the second surface. For the second surface, based on the way it is curved, we can tell that the center of curvature is on this side. the negative side. So the radius of curvature of the second surface should be substituted negative in the formula, minus 10. That's all. So you get 1 by f is equal to 3 by 2 minus 1 is 1 by 2. And inside you have 1 by 20 plus 1 by 10. That is 3 by 20. That's 1 by f. Therefore, the focal length of this lens is 40 by 3 centimeters. That is 13.33. Okay. Now we got a positive focal length. What does this mean? This means the parallel rays, after passing through the lens, meet on the positive side. Okay. The positive side is the right side. Rays are also going to that side only. So center is 20, 13.33 maybe somewhere here. So what is going to happen is the light rays will bend twice. Okay. Once they'll bend on the first surface, then again they'll bend on the second surface. Okay. But in case of a lens, when drawing ray diagrams, we don't show the rays bending twice. What we do is we extend the incident ray up to the middle of the lens. It should actually bend on the first surface. It should bend again on the second surface. But to avoid time waste, this is how we draw the ray diagrams. We extend the ray all the way to the middle of the lens. And from there, we draw the emerging ray. Okay, the final ray that comes out of the lens. So this is one ray for us. And this is the other one. This point is the focus. And we got focal length as 40 by 3 centimeters. Okay, so it's fine. This I think is quite easy. Any doubts in this? Okay. Now look at what this particular lens did. See, it was a convex lens, convex on both sides. When parallel rays are incident on it, okay, rays parallel to the principal axis are incident on it, it is bringing the rays together. So it's showing a converging behavior. So we call it as a converging lens. Okay, it tends to bring light rays close to each other. Okay, so it's a converging lens. Fine. Now we assumed rays are incident from the left side. S1 was the first surface, S2 was the second surface. We got focal length as 13.33, 40 by 3 centimeters. Focus was on the right side. Positive focal length. Same situation. What do you think will be the focal length if light is incident from the right side? Any idea? How much do you think the focal length will be if light is incident from the right side? Refractive indices and all are same. Direction of propagation of light is different. And what will the lens behave like? Anugrah, any answer?
Sir, would it be minus 40 by 3?
Okay, we'll see. We'll see. Any other answers, anyone? Okay, solve this as a question now. Rays are incident from the right side. And if rays are incident from the right side, the right surface will be the first surface this time. So this side will be S1, then 10 centimeters is the magnitude of R1. Okay, sign you still have to consider. The other surface will be S2 and 20 will be the magnitude of R2. Apply the formula once again and find out the focal length. Make it fast, all of you. Okay. Yeah, Anugraha, your answer is correct only. right? Direct substitution. In the formula for focal length, that lens maker formula, n2 is the refractive index of the lens, n1 is the refractive index of the medium outside the lens. So again, it becomes 3 by 2 minus 1 whole divided by 1 multiplied with 1 by R1. Shashank, can you tell me how much we should substitute R1 as?
Plus 10.
Plus 10, correct. Incident rays are traveling to the left. So any distance to the left of the lens is positive this time. Any distance to the right is negative. And the center of curvature of the first surface is on the left side, C1. So it will be plus 10 minus 1 by R2. Center of curvature of the second surface is on the right side. C2. Right side is negative, so minus 20. Again, 3 by 2 minus 1 is 1 by 2. Into 1 by 10 plus 1 by 20 is 3 by 20. You get the same result again. 1 by f is 3 by 40. So focal length is again 40 by 3 centimeters. But when light is incident from the right side like this, traveling to the left, the focus will be on the left side because this is the positive side now. Okay. So not just in this case, in any case, a lens always has two foci, one on that side and one on this side. Which one you consider while solving a problem, which one you consider while drawing a ray diagram, depends on the direction in which the incident rays are traveling. Okay, if the object is on the right side for this particular lens, if the object is on the right side, then focus should be taken on the left side. And if object is on the left side, you should take focus on the right side. And observe, its behavior is still the same. The focal length is the same, and what it is doing to the light rays is also the same. It's still a converging lens. Okay, and it's not a coincidence. You consider any lens you want. You take light incident from one side, find out the focal length. You assume light incident from the other side and find out the focal length. You will always see that they are the same. Okay, so for a given lens, there will be only one focal length. Which focus you consider while solving the problem depends on the direction in which the light rays are incident, but the distance is the same. Okay, the focal length is the same. Okay, one lens has one focal length only, depending on the medium in which it is placed. Okay, now this particular lens tends to behave as a converging lens. Now, what lens did we consider? A biconvex lens. Let us generalize its behavior. Now we have seen that whether you take light incident from left side or right side, focal length is the same. So let's assume light is incident from the left side itself. Assume this surface radius is R1, this surface radius is R2. Inside the lens, the refractive index is N2, outside is N1. Then from the lens maker formula, you get 1 by f is equal to N2 minus N1 divided by N1 into 1 by R1 minus 1 by R2. Now, if you assume light is incident from the left side, this becomes the first surface. Right direction becomes positive, left direction becomes negative. You'll substitute R1 positive and R2 negative. Okay. If you substitute R1 positive and R2 negative, this second bracket will always be positive. Okay. Even when light is incident from the other side, that second bracket will be positive only. So for a biconvex lens, generally what we call as a convex lens, that second bracket is always positive. 1 by R1 minus 1 by R2. N2 minus N1 could be positive or negative, depends on the medium in which the lens is placed. Depending on the medium in which the lens is placed. Okay. So there will be two cases. First case, if N2 is greater than N1, what does that mean? Lens material is denser than the medium surrounding it. Okay. For example, a glass lens placed in air. Okay. If n2 is greater than n1, the first bracket will become positive. Second bracket is anyway positive. That means the focal length will be positive. And if focal length is positive, what does it mean? The light rays will meet on the side to which they are traveling, means on the other side they will meet. Then it becomes a converging lens. Okay. Second case. Suppose n2 is less than n1. What does that mean? Lens is made of a material whose refractive index is less than the medium outside. Okay, that is also possible. In that case, the first bracket will be negative, second bracket is anyway positive. Then the focal length becomes negative. What does focal length becoming negative mean? It means the point of convergence of the refracted rays is on the same side as the incident rays. Okay, how is that possible? In that case, what happens is light rays or parallel rays traveling like this, they go away from the principal axis. So they appear to be coming from somewhere on the same side as the incident rays. That is what we mean by negative focal length. And in that case, what is the lens doing to the rays? It is diverging them. So it behaves as a diverging lens. So what I want you all to understand and remember is that a convex lens can be converging, it can also be diverging. Okay, just based on the shape of the lens, you can't say anything. You need to know the refractive index with which the lens is made and the refractive index of the medium outside the lens also. Okay, but generally, positive focal length indicates converging lens. Whether it's convex, concave, plano-convex, plano-concave, concavo-convex, whatever it is, if focal length is positive, it's a converging lens. And if focal length is negative, it's a diverging lens. That is general behavior. So convex lens can behave as converging as well as diverging. Okay. Let's try another problem. We'll take a concave lens this time. Okay, by concave. Now, which side you assume the light to be incident from is your choice. Okay. As I said, it doesn't matter from which side the light is incident. The focal length of a lens is the focal length of a lens. It only depends on the radii of curvature and the refractive indices. It doesn't depend on direction in which the light is traveling. Where exactly you take the focus depends on the direction of propagation of light. So it's concave on both sides, as you can see. Let's say this radius is 20 centimeters and the other side radius of curvature is 10 centimeters. Wait, this time, assume the refractive index outside the lens is higher. Let's take it as 2. Outside the lens, the refractive index is 2. Inside, it is 3/2. Derive its focal length. Make it fast, solve carefully. Okay, I got one answer as plus 80/3 centimeters. Let's see. Rishi, unmute, we'll discuss.
Yes, sir.
Tell me the formula, lens maker formula.
N2 minus N1 by N1
Left hand side.
into,
Left hand side first.
1 by F is equal to N2 minus N1.
Because many times in a hurry, like especially in exams, students make that mistake also. Left hand side, instead of taking 1 by F, they take F. And the same mistake they do in case of finding out resistance in parallel also. 1 by R is 1 by R1 plus 1 by R2, but in a hurry, students take 1 by R1 plus 1 by R2 is equal to R. Okay. Anyway, it's always better to tell the entire formula. So n2 minus n1 by n1, continue.
Into 1 by R1 minus 1 by R2.
Okay. From which side did you assume the incident rays to be
Left
falling on
side,
the
sir.
lens? Okay. Fine. So if you assume incident rays are traveling from the left side towards the lens, then this is the first surface, this is the first radius, and this is the second surface, and this is the second radius for us. Fine. So n to n1, it's obvious. 3 by 2 minus 2 whole divided by 2 into. Rishi, tell me, how much will you substitute R1 as?
20 only, sir.
Why?
Sir, because the incident rays are moving from the left to the right.
Incident rays are moving from left to right, so you'll, based on that, you will decide which is positive. R is radius of curvature. No, radius is a distance from where to where. So you are saying just because the incident rays are like this, R1 will always be positive, irrespective of whether the lens is concave or convex. You will take R1 the
No,
same.
sir. No, no,
Depends
no.
on the curvature, no? Incident rays are coming from the left side, they are going to the right side. So anything on the right, any distance on the right will be considered positive. Any distance to the left will be considered negative. Now tell me whether R1 is positive or negative.
R1 is negative.
Negative. Okay, because the center of curvature of the first surface is on the left side. So you'll have to substitute minus 20. Minus 1 by, what about R2?
Positive only, sir. 10.
Positive, because the center of curvature of the second surface is on the positive side. So plus 10. Okay. Fine. 3 by 2 minus 2 is minus 1 by 2. Divided by 2 is minus 1 by 4. Multiplied with minus 1 by 20, minus 1
Minus
by
3.
10 becomes minus 3 by 20. Minuses cancel, you get 3 by 80. Therefore, the focal length is 80 by 3 centimeters and it's positive. What does a positive focal length suggest? Any of you? What does a positive focal length mean?
Sir, that the rays meet on the positive side.
Okay, it's a converging lens. The rays meet on the positive side. 80 by 3 is 26 point something. Okay. As I said, in case of lenses, we extend the incident ray up to the middle of the lens. And they converge onto the principal axis. And meet at a distance of 80 by 3 centimeters. Now, what kind of a lens is this? Like based on its shape, not based on its behavior. Based on the shape, what kind of a lens is this? Concave lens. Biconcave, both sides concave. Simply we call it as a concave lens. And it's behaving as a converging lens. It's possible. Concave lenses can behave as converging. They can behave as diverging also. It all depends on the refractive indices. Okay, so let us generalize the behavior of a concave lens. We know that the focal length will turn out to be the same whether you take light incident from the left side or from the right side. Okay, so let's assume light is incident from the left side like this. Then in the lens maker formula, 1 by f is equal to n2 minus n1 by n1 into 1 by r1 minus 1 by r2. If it's a concave lens like this, biconcave lens, r1 will be negative, r2 will be positive. Now r1 value is negative, R2 value is positive. let it be, but R2 also has a negative sign in the formula. Therefore, this bracket will always be negative. The second bracket will always be negative in case of a concave lens. Now the focal length, the sign of the focal length would depend on the sign of the first bracket. Okay, so first case, if N2 is greater than N1, which is the most common case. Usually we use lenses in air itself. Okay, N2 is more than N1 means lens medium or lens material should have a higher refractive index than outside. So it's like a glass lens placed in air. Common case. In that case, the first bracket will be positive. Second bracket is always negative. It means the focal length becomes negative. Focal length negative means it's a diverging lens. So commonly, a concave lens behaves as a diverging lens. But that's not always the case. If N2 is less than N1, that means if the concave lens is placed in a medium which is denser than the lens itself, like the example that we have just taken, first bracket negative, second bracket negative, on the whole, the focal length will become positive and it behaves as a converging lens. Okay, so whether a lens is converging or diverging, you will tell based on the focal length, not based on the shape of the lens. Okay. And because a single lens, a particular lens, can behave either way depending on the medium in which it is placed, in lens-based questions, they will have to give you the focal length along with the sign. Okay. They can't just say a focal length of, a convex lens of focal length 10 centimeters and expect you to know whether to substitute plus 10 or minus 10. Okay, because convex lens can have plus 10 focal length, it can have minus 10 also. So they will, whatever focal length they give, you'll have to substitute as it is in the formula. In case of mirrors, it is not like that. In case of mirrors, especially for a concave mirror, if they say focal length is 15 centimeters also, you will have to substitute minus 15 because concave mirror must have a negative focal length. And convex mirror must have a positive focal length. Okay, but for lenses, it's not like that. So whatever focal length they give in the problem for a lens, that will be used as it is. Okay, you can't decide whether it should be plus or minus. If they have given plus, use plus. If they have given minus, use minus. Okay. Next, how many of you use specs? Just raise hand or say yes in chat. One, two. Okay, I want you to observe the lens of your specs. Describe its shape, the inner surface and the outer surface. What do they look like? I mean, are they concave or convex is my question. Okay, inner surface is concave, outer surface is convex. It makes sense because otherwise it will become difficult for the eye. Just a moment. The lens of lens of the specs that you use, you means especially people of young age. Okay, the lens of the specs that you use will be shaped like this. Inner side has to be concave because the lens should not touch your eye. Okay, there should be a safe distance between your eye and the lens. So inner side will be concave. outer side will be convex. They can actually keep the outer side concave also. Okay, you think about why they make the outer side convex. But what about the radius of curvature? Okay, I have just copy pasted some image from the internet. The ones who use specs, see and tell me which side of the glass do you think is curved more, means has a lesser radius of curvature? The concave side or the convex side? Okay, yeah, Pradyun, your answer is correct. Like I can tell you without seeing your specs also, because mostly people of your age, okay, 16, 17, what is the defect in your eyesight? What is it called? Myopia. Myopia. Okay. Old people get hypermetropia. Young people, mostly they will be having myopia itself. Okay. And for myopia, correction of myopia, this is the kind of lens that is used. And Pradyun has given me the answer. The inner surface is more curved compared to the outer. Okay. So the concave side has a smaller radius of curvature than the convex side. Fine. Let's consider a lens like this. Derive its focal length. Assume it is in air. I'll give you the radii of curvature. Okay, inner one is more curved, less radius of curvature. So let's take it as 10 centimeters. Outer one is relatively flatter, much bigger radius of curvature. Let's take 20 centimeters. Refractive index of glass 1.5. Outside is air 1, 1. Derive the focal length. Any answer? Okay, let's see. We'll directly substitute. I got one answer as minus 40. Fine. 1 by f is equal to n2 minus n1. 1.5 minus 1 is 0.5. That is 1 by 2. Divided by n1 is 1. I'm not writing it. Into 1 by r1 minus 1 by r2. It doesn't matter from which side you assume the rays to be incident. Okay, usually the light that enters into your eye comes from outside. Okay, from the convex side. So let's take it like that only. Let's say light is incident from that side. Then this becomes r1. This becomes r2. Which is r1, which is r2 depends on which way you take light to be incident. So this becomes the positive side. The other is negative. Fine. So 1 by r1. Now for that flatter surface, okay, which is convex, the center of curvature is on the left side. Okay, in fact, for both of them, the center of curvature is on the left side only. C1, C2. Okay. So positive 20 minus 1 by R2. R2 is also positive 10. Both surfaces have their centers of curvature on the left side. That's all. So it becomes 1 by 2 into 1 by 20 minus 1 by 10 is minus 1 by 20. Therefore, the focal length becomes minus 40 centimeters. Why are the others always taking so much time to solve this? Like in all three questions that I have asked, Anugraha has given the first answer. Just see and substitute carefully, okay? Any doubt in this? How to substitute? Rishi, did you understand what to substitute and how to substitute?
Sir, I keep going wrong in what to take positive and negative, sir.
Are you visualizing the incident rays? That is the
Yes,
first
sir.
thing you need to do. Once you visualize incident rays, you assign one side positive, one side negative, and then you have to imagine the surface to be part of a sphere like this. Then you will be able to clearly see on which side its center lies. And on whichever side the center of curvature of a surface lies, based on that you substitute positive or negative. Shashank, what about you? Any doubt?
No, sir.
Okay. Pradyun? Fine, fine. Okay. We're getting focal length negative means what kind of a lens is this? Converging or diverging? Negative focal
Diverging.
length always means diverging lens. Okay. For correcting myopia, what you need is a diverging lens itself. Okay. We'll discuss defects of eye in detail. Okay. So if a lens is shaped like this and it's present in air, that is the most important thing. If you dip that lens in water, no, its focal length will change. And you all must be aware of something called power of a lens. Okay, let us discuss that also. This is not the mechanical power, energy transferred per unit time or work done per unit time. Power of a lens is nothing but its optical power or the refracting power. Basically, the ability of a lens to bend light. Okay. If a lens bends light very sharply, then its refracting power will be high. If a lens doesn't bend light that much, then its refracting power is less. So it's the ability of a lens to bend light. Okay. Now, the focal length of a lens depends on how well it can bend the light. And power of a lens is determined by how well a lens can bend the light. So power should be related to focal length. Fine. And if focal length is small, what does small focal length mean? I'm talking magnitude wise, okay, not along with the sign. Suppose the focal length is very short. Okay, let's consider a converging lens itself. Suppose two rays are incident, two parallel rays. And assume its focal length is very short, means it bends light very sharply. Okay. So short focal length means higher amount of power. Magnitude wise, I'm not talking along with the sign. Okay. So short focal length, more power. Long focal length, less power. Long focal length means the light is not bending that much to converge at a short distance. Then that means it has less refracting power. Okay. So power and focal length are inverse of each other, inversely proportional. By definition, they are actually inverse of each other. That's all. So power P of a lens is nothing but the inverse of its focal length, refracting power. Okay. So this is basically the ability of a lens to bend light. Okay. And focal length is a length. We like usually in problems we'll get it in centimeters, but the SI unit of length is meters. If focal length is in meters, then power will be in meter inverse, which is what we call as diopter. Okay. Rishi, what is the power of the lens that you use?
-3, sir.
-3. Okay. See, those of you who have myopia, you all use lens of this kind itself. And all of you are using those lenses in air only, no? Any lens of this, a lens of this kind used in air will have negative focal length. Okay. And if focal length is negative, automatically the power will also be negative. Fine. So all those people who have myopia will be using lens with negative power. Okay, negative focal length, negative power. Fine. So hope you understood the basic behavior of lenses. Lenses can, a particular lens itself can behave as both converging or diverging depending on the medium in which it is present. In fact, in some cases it may not do anything, means it may not bend the light at all. In which case does that happen? If n2 is same as n1. If the refractive index of the medium outside the lens is same as the refractive index of the medium with which the lens is made, then there won't be any bending of light at all. So it's like the lens doesn't even exist. It's the same medium throughout. Optically, it's the same medium throughout. So no bending of light will take place. Okay. Fine. Next, cases of image formation by lenses. But before that, we'll have to derive the magnification formula. Let us do that. Magnification by a lens. Or do we need to do this? No. Magnification we'll discuss tomorrow. Let's discuss cases of image formation by a lens. So first we'll take converging lens. See, I'm using a convex lens. I don't mean to say that a convex lens is always a converging lens. Let's say in this particular situation, its behavior is converging behavior. I could have used a lens of any shape actually. Okay. Convex, concave, concave or convex, anything. So assume this thing's focal length is positive. And let's say object is placed on the left side. If object is placed on the left side, rays will be going to the right. Focal length is positive, means the focus will be on the right side. Why do we care about the focus? As I said, it helps us in ray diagrams. For now, actually, okay, we don't exactly need a ray parallel to the principal axis and all. Let it be. Assume the focal length is positive. Let this be the focus. You can mark the same distance on the other side as well. Okay, just mark it. I don't mean to say that this is a focus, but you can mark the same distance, mark a point at the same distance on the other side. Assume there's an object placed somewhere here. Let's take some distance, maybe, okay. Let's assume the focal length first is 10 centimeters. And let's take the object at 40 centimeters on the lens. Okay, this doesn't look like 40. Let it be. Find out where the image forms. You know the lens formula, 1 by V minus 1 by U equal to 1 by F. We derived it today itself. Substitute directly and tell me the image location. Be careful, you'll have to use sign convention when you substitute. Rishi, how much are you getting V as?
Sir, 40 by 5, 8.
40 by
5.
40 by
8
5
basically.
you got. Where did 5 come from? Okay, let's see. Tell me what you substituted. 1 by V minus, how much is U?
Sir, 40.
Yeah, I reminded you also, you have to use sign convention. Rays travel from the object towards the lens. So anything on the right side is positive. Any distance on the left is negative. Object is on the left. And I told you this before also. For a real object, the object distance is always negative. Whether it's a lens or a mirror doesn't matter. If the object is a real point, the object distance will always be negative. Okay, you substitute minus 40 there is equal to 1 by f. And I told you for lenses, whatever focal length they give, you have to use it as it is. You can't tell whether it should be plus of that or minus of that. Okay, so send it that side. You get 1 by v is equal to 1 by 10. Here it's plus, that side becomes minus 1 by 40. So 4 by 40 minus 1 by 40, 3 by 40. You get v as plus 40 by 3 centimeters. 40 by 3 is 13.33. So it will be beyond the focus on the other side at a short distance, maybe somewhere here. This is where the image of the orange dot forms. Okay. Let's try another case. Assume object is somewhere here. Focal length is 10. So let's take object distance as 15. Okay, solve quickly and tell me the image distance. Object distance is 15 centimeters. Substitute carefully. Okay, 1 by v minus 1 by u is minus 15 is equal to 1 by f. So 1 by v becomes 1 by 10 minus 1 by 15. 10, 15 LCM becomes 30. 3 minus 2, 1 by 30. You get v as plus 30. Okay. Focal length is 10. Twice of focal length will be 20. 30 will be beyond that. Somewhere here. For the green dot, this is the image. Let's call it I2. Object is O2. Okay. Now, what kind of images are these? Both I1 and I2. Are they real or virtual, or you cannot say? Anugraha, tell me, when do you call an image a real image?
When the light rays converge after refraction.
Okay. When light rays actually pass through the image location, you call it a real image. Because if you put a screen there, light falls on that screen and you can see the image. Fine. Now, we are now discussing refraction by a lens. Light is incident from the left side. The object is on the left side. Light rays travel to the right. They pass through the lens and go to the right side. We are looking at image formation by refraction, not reflection. So rays actually travel to the other side of the lens. And if image is forming on that side, it has to be a real image. Fine. So both I1, I2 are real images. And I told you one property in the first class itself, first class or second class. When a real object forms a real image, their positions get interchanged. You can take object to image position, image will come to object position. Okay. Now see what has happened here. First case, we took object distance 40. Where is the image forming? 13.33. 13.33 is between f, the focal length, and 2f. Because focal length is 10, 2f is 20. 13.33 is somewhere between those two. Okay. So if object, okay, from a converging lens, we are discussing properties or image formation by a converging lens. If object is at a distance greater than 2f, okay, for the object O, the object distance is greater than 2f in magnitude. 2f is 2f is 20, object distance is much greater than that. Image forms between f and 2f. Fine. And if this becomes the object, then this should become the image. That means if object is between f and 2f, image should be beyond 2f. And that is what has happened with the green dot. Okay, we didn't actually interchange places. We just took another object, which is between f and 2f, between 10 and 20 centimeters from the lens. We took 15 exactly. And where did we get its image? 30 centimeters. It is beyond 20. So if object is between f and 2f from a converging lens, image will form beyond 2f. Okay. This will help you in visualizing situations easily, and especially cases where object is moving, image is moving, it'll make it easy for you to tell what is going to happen. Okay. So object beyond 2f, image between f and 2f. On the other side, real image. And if object is between f and 2f, image will be beyond 2f. On the other side, real image. Okay. What if, like, just by looking at this, I think you can tell, what if the object is exactly at 2f? Where will its image form? You can use the formula. You can substitute in the formula and tell me. Suppose there's an object at 20 centimeters from this lens on the left side. Find out where its image forms. Rishi, substitute quickly and solve.
Sir, if f is 20,
Not f is 20. Object distance is 20. And you decide whether you have to substitute plus 20 or minus 20. F is 10 itself. See, all this visualization will help you in deciding which lens is to be used in which case to serve a particular purpose. Okay, like in this chapter itself, we have optical instruments. Okay, microscope, telescope, which lens to use in those and all, you'll be able to tell based on these properties. And which lens myopic should be used to correct myopia, which lens should be used to correct hypermetropia. Those things also you can comment on those things if you know the types of images that they can form or the different cases of image formation that are possible.
sir, v is 20.
You're getting V as plus 20, correct. And 20 is nothing but 2f. Okay. So if object is at 2f on one side, image forms at the exact same distance 2f on the other side. Okay. So this is one case where object distance is same as image distance and they are on the opposite sides of the lens. This happens with a converging lens. Okay. So you can have object distance equal to image distance also, but they'll be on opposite sides of the lens. So if object is beyond 2f, image will be between f and 2f. If object is between f and 2f, image will be beyond 2f. If object is at 2f, image will also be at 2f. And we are left with one more case. What if the object is within the focal length? Solve this quickly, all of you. Suppose there's an object at 5 centimeters, at a distance of 5 centimeters from the lens. Find out image position.
Sir, is it 3.33?
No, it won't be positive. How much did you substitute object distance as?
Sir, 5.
You are supposed to take it minus 5. No, I told you for
No,
a
no,
real.
no, no, I took it as minus 5. Yeah, I took it as minus 5.
Okay, let's see. 1 by V minus 1 by U is equal to 1 by F. Send it that side, it becomes minus 5, minus 1 by 5. So 1 by V is equal to 1 by 10 minus 1 by 5 is like minus 2 by 10. You get minus 1 by 10. That means V is minus 10. And what does the minus sign indicate? It indicates that the object is on the, the image is formed on the left side itself. And interesting, we got minus 10. Means it's forming exactly on this focus. Anyway, that is not the actual focus for this problem, because when object is on the right side and focal length is positive, the actual focus is this. We just indicated a distance f on the left side, okay, to know where the image is forming or where the object is placed. And we see that when object is at 5 centimeters, image forms here. Possible? Okay, let's finish this quickly. Generally tell me, if object is at the focus, exactly at the focus, where does the image form? If object is exactly at the focus, where does the image form?
At infinity.
At infinity, correct. It's true for mirrors and lenses also. Okay, so same thing happens here. If the object is placed at a distance equal to focal length on the left side, not the right side. If you put it on the right side, then rays will be going to the left. All the things will get reversed. So if object is exactly here, what happens is the rays after passing through the lens tend to go parallel to the principal axis like this. Okay, so to someone on the other side, they'll appear to be coming from infinity. That is what we mean by image forming at infinity. So if object is at the focus, image forms at infinity. That's fine. You bring the object within the focal length now. Okay, at a finite distance, maybe somewhere here first, just slightly within the focal length. Then you will get an image somewhere far on the same side. Okay, if this is object, this is image. You keep bringing it closer to the lens. You put it at exactly f by 2, 5 centimeters. If that is the object, image forms at f. And you bring it even closer, maybe here, then the image will also come even closer. That also you can try if you want. You take object distance minus 2.5 and see where the image forms. Okay, so if object is within the focal length, as the object comes towards the lens, image also will come towards the lens on the same side as the object. And if image is on the same side as the object, it's a virtual image. So converging lenses can form virtual images also. When the object is placed within the focal length, they form virtual images on the same side as the object. Okay, for the yellow object, this is the image. For the purple one, this is the image. For the orange one, this is the image. Okay, image forms beyond the object itself, but on the same side, it's a virtual image. It can be anywhere depending on where you put the object. It's not necessary that image should always form outside the focal length. It can form inside the focal length as well. In fact, when the object goes very close to the lens, object position itself will become the image position. Okay. Fine, we'll stop it here for today. So what we discussed today is basically application of spherical surface refraction formula to a lens. We derived the lens maker formula and the lens formula. Then we applied it. We found out focal length. We discussed the behavior of lenses. Convex doesn't always mean converging. Concave doesn't always mean diverging. But commonly they do, because commonly we use lenses in air. Okay. Then we talked about power of a lens, inverse of its focal length, and different cases of image formation by a converging lens. Okay, let's talk about diverging also, just one more case. In diverging, there will be only one possibility. Let's finish that. So consider a diverging lens. Just by looking at the lens formula, you can tell what is the only kind of image that it can form. Again, a concave lens doesn't always mean a converging lens. Sorry, doesn't always mean a diverging lens, but usually it does. So assume this is a lens having negative focal length and there's a real object placed in front of it, somewhere in front of it. Okay. Let's call the object distance as x. X is the magnitude. When you substitute in the formula, you are supposed to substitute along with sign. Okay. Substitute in the lens formula. 1 by v minus 1 by u is equal to 1 by f. So you get 1 by v is equal to 1 by f minus minus becomes plus minus 1 by x. Now x is a positive number. That's fine. But it comes with minus. Okay. So minus 1 by x is a negative term. And this is a diverging lens. Focal length is anyway negative. Then this whole thing will be negative. What does that mean? Image forms on the same side as the object. Always a virtual image for a real object. This is the only possibility in case of a diverging lens. Okay. And where exactly it forms? Let's quickly solve one problem. Assume the focal length of the lens is minus 20 centimeters. And let's say the object is at a distance of, I'm giving you along with the sign, let's say minus 40 centimeters. Quickly tell me the image distance. You can start writing it this way. 1 by v is equal to 1 by u plus 1 by f. Instead of writing minus 1 by u on this side, then sending it that side. It becomes 1 by minus 40 plus 1 by minus 20. 1 by 20 is like 2 by 40. Effectively, it becomes minus 3 by 40. You get image distance as minus 40 by 3. That is minus 13.33. Object is at 40 centimeters from the lens. Image is at 13.33 centimeters from the lens. Means image is closer than the object. And this is always the case in case of a diverging lens. Image will be closer than the object. That is why people having myopia are given, that is why a diverging lens corrects myopia. What is myopia? They can see nearby objects, but they can't see faraway objects because their eye is not able to adjust its focal length to form an image on the retina of the faraway objects. So what the correcting lens does, okay, or the specs, what the specs does is it forms an image of a faraway object close to your eye so that your eye will be able to see it. That's all. Okay, and that is the reason diverging lenses are used. Okay. Fine. So converging lens, there are multiple cases of image formation. If object is beyond 2f, image forms between f and 2f. If object is between f and 2f, image forms beyond 2f. If object is exactly at 2f, image also will be at 2f. If object is within the focal length, image will be on the same side as the object, any distance. Depends on the situation. Okay. But for diverging lens, there's only one possibility. Image will be closer than the object, and it will always be a virtual image if the object is real. Fine. So next class we'll discuss problems based on refraction at a single surface and also refraction by lenses. We'll become perfect in all this. Okay, thank you all. We'll continue in the next class.